Just little bookkeeping things here before we get going. So I looked at the submissions for the syllabus sign-in sheet, and it seemed like a couple of us missed that deadline or whatever, or hadn't gotten that in. I'll extend that out, to cover tonight also. So if you didn't get your syllabus sign-in sheet uploaded to PowerSchool last night because you forgot or what you ran into trouble or whatever, I'll extend that deadline out here another day or two. So if you didn't do that, make yourself a note right now so that you remember to do that. I think there was, I don't know, like 6 people or something that missed the deadline. It wasn't a ton, but if that was you and didn't get that into PowerSchool, make yourself a note to try to take care of that tonight. And somebody emailed me about trouble downloading the syllabus or whatever, and I sent them something back. Everything should work. I tested it out again this morning, so I don't think it shouldn't be a problem, but okay. Good. So today we're going to kind of get started here, and we'll have like a little bit of a soft start because we're not going to dive too deep into anything here on the first day, but I want to start with just a little bit of a like a refresher from what we remember from our algebra course. And I know that was a long time ago, so I don't want to, like crazy expectations, because I mean, what was the start of your Algebra 1 course was 2 years ago, basically? So I know that's a long time ago, and I know that there'll be stuff that you don't really remember that you remember, or you won't maybe remember the names for things right away or any of that, and that's all fine. Like, this little phase, there's really no wrong answers. It's mostly to kind of get you guys your memories jogging and give me an idea of kind of what we remember seeing. But basically what I want to do is just kind of talk about things that you remember doing in your Algebra 1 course, and I'd like this to kind of be, directed from you guys. So if there's something that you remember from your Algebra 1 course, let me know. We'll kind of write it down, talk about it a little bit. And if there's things that somebody says that they did during their Algebra 1 course, and you're like, dude, I didn't do that, it's not a big deal. Like, there's going to be some things that some of us did that others of us didn't, depending on like the quality or what grade you took it in. Like, if you took Algebra 1 as an 8th grader and the 8th grade year ended early, there's maybe some stuff at the end that if you took Algebra 1 as a freshman that you did that the other class wouldn't have, and all that kind of stuff. So like, don't be freaked out if there's stuff that some people said they remember doing that you didn't do. Like, we'll talk about the things that I'm planning on redoing, and the stuff that I wouldn't plan on redoing, or where the expectations are and that sort of stuff. So, again, there's no wrong answers here. I don't want to freak anybody out about, like, if somebody's like, oh, I did this in Algebra 1, and you're like, I didn't do that. It's probably fine. Okay? So any volunteers? Anybody at all? Anything you kind of remember doing? And even if you don't remember the name, if you can kind of describe it, we'll put a name to it. Yes, sir. Okay. So probably when we talk about solving equations in Algebra 1, you probably mean linear equations. Like ax plus b equals c kind of things. And I think that really everybody should remember doing this in their Algebra 1 course. And my expectation is you could do this kind of a problem. This would be considered a pretty easy problem for, the vast majority of us. But absolutely, that's something you would have spent a good deal of time, especially the first semester of Algebra 1, kind of getting pretty good at, if not in other classes before. This is often a pre-algebra topic as well. Good. Who else? Yes. Great. So slope, for sure. And probably you remember talking about slope as rise over run, or as the equation y2 minus y1 over x2 minus x1. Yep. Again, I think regardless of when you took your Algebra 1 course or where you took it at, that's something that's covered in Algebra 1. I think also you touch on it often in a pre-algebra course also. So that's something you probably have seen a couple of times, not in including your geometry class from last year, which it probably came up again on. For sure, on that same vein of slope, what else do we often talk about right when we're talking about slope? Graphing a, what do we use slope to graph? Line, yup. So like y equals mx plus b. Or the other thing we might use slope for is writing the equation for a the same answer for line. And again, regardless of kind of when and where you took your Algebra 1 course, these are things that you should remember doing. If not, also done in geometry. I think you do both of those two topics again in geometry to some extent, right? Like if we give you 2 points, you can write the equation for a line. Those two, that kind of a skill doesn't come up a ton in this course, although we do spend a good amount of time graphing things other than lines and writing the equations for functions other than linear functions. So this type of problem is really comes up again over and over in an Algebra 2 class or a second year algebra class, although we don't necessarily spend a lot of time talking about graphing lines or writing the equations for lines. We do spend a lot of time, though, graphing other kinds of functions and writing the equations for other kinds of functions, which again, the line, doing this for lines is a nice introduction to those kind of methods. Good. What else do you guys kind of remember? There's a couple of big acronyms that should kind of be familiar here. Yes. Yeah. So certainly you would have spent some time talking about the order of operations. And I think some of us do PEMDAS with an E there, and some of us do it with an O. So parentheses, exponent, multiplication, division, addition, subtraction. That E for exponent, there's a lot of other things that could go there where exponent is, like square roots or sine, cosine, tangent. So a more general description of that order of operations would be POMDAS with an O there for operation, where it's a placeholder for exponents or square roots, or like lots of other sorts of things that could go there. But probably PEMDAS is what you guys remember seeing. I think this gets introduced before any of those other operations, so it probably stuck as PEMDAS. But yes, the expectation would be that you are familiar with the order of operations and you can do that successfully. Now, on occasion, are you going to make mistakes in the order of operation? Sure, especially when we introduce like new sorts of operations and like things get a little bit complicated. That's okay. The expectation, though, is if we point out that you're violating the order of operations and why that's happening, you would maybe be able to make that correction, and it would not be a mistake you'd make over and over and over again once we kind of establish that, hey, doing it, what you're doing right there violates the order of operations, and this is why. You would be able to recognize doing that in the future and not do it in the future. But on occasion, like specifically, there's some stuff when we talk about rational functions where it's really easy to think that, oh, I can just do this, and you're like, no, you can't do that. As it's an order of operations issue, but it's sometimes subtle to see it right away. Good. There's a couple of more. There's another big acronym that you would have spent some time dealing with in Algebra 1 class. Starts with an F. Well, functions, certainly you would have spent some time talking about. Sure. That's not the F that I was thinking about, but it's a good F. Foiling was the acronym that I was thinking of. And foiling is just an acronym describing how you multiply two binomials together. So it stands for first, outer, inner, last. So we multiply the first terms together, and then the outer terms, and then the inner terms, and then the last terms. So in terms of functions, I would have hoped that most of us at least heard this term function before in your Algebra 1 class. This is actually we'll start this course with a really general definition of what a function is and talk about like what kinds of things are functions and aren't functions and how you can kind of figure out if something's a function or not. So this is really going to kind of be our starting point. So even if you didn't remember spending a lot of time talking about functions, or you can't really remember the definition of a function, that's okay, because this is kind of ground zero where we're going to start this course off. So you probably did talk a little bit about functions and function notation, but we're going to get a lot more of that here to start. And really this Algebra 2 course is going to be mostly a survey of functions. So we're going to talk about these different kinds of function groups and how we do certain kinds of tasks with each one of these function groups. And it'll be really the same set of tasks over and over and over again, but applied to a different set of functions. And then foiling, again, the expectation is that you guys have foiled before and you can do this successfully. We will extend this idea of foiling that you guys would have done in your Algebra 1 class to include, like bigger types of polynomials. So things that aren't necessarily linear and things that would have more than two terms. Some of the methods we can use to kind of keep track of everything there. You can use the same general idea as FOIL, but if you have 4 or 5 terms in your polynomials, it gets a little bit hairy kind of keeping track of everything, and we'll present some methods that make that a little bit easier to deal with. But foiling is kind of like the basic level, and we'll kind of extend out that idea of how to multiply two polynomials together. It's maybe a little bit easier to keep track of all the terms involved. And there's one more F word that I'm hoping that many of us did during our Algebra 1 that's related to foiling. Factoring, yes. So there's probably 2 types of factoring that you're familiar with. There's just where we use it, or where we take out a greatest common factor. Where if we have something like 3x squared plus 2x, we notice that there's an x in common to each of those terms. So we can factor the x out, which is basically what we're doing is just the reverse of the distributive property, right? The other type of factoring that you would have possibly seen is on a quadratic. So for example, if you had something like x squared plus 7x plus 10, you could factor that to x plus 5 times x plus 2. Now I notice that here I didn't explain at all how I did that. Some of you probably remember how to do that. Some of you may not have. It's usually, a half to 2/3 of the students are familiar with this kind of factoring and are reasonably good at it already. My assumption, though, is that we're going to reteach this from a general standpoint anyways, because it's been a while, and of the first semester skills, the ability to factor quadratics quickly and accurately is probably the one that is the most important going forward, because you'll use it a ton in second semester. You'll use it a lot in your trigonometry and pre-calculus class and calculus class. It's a really important skill to be good at. So we will kind of take some time and make sure that we're kind of starting from ground zero as to not leave anybody behind on something like that. And there's actually 2 types of quadratics that are possible to factor. So if we have something like this where the leading coefficient isn't 1, the factoring's a little bit harder. Still doable in many cases, but a little bit harder. And some of you may have even done this kind of factoring in your Algebra 1 class, although I'm guessing that less of us that did remember doing factoring, remember dealing with things that didn't have a coefficient of 1, because it's a little bit more complicated. But there is one general method that works in either case. And that's what we'll kind of start with, is presenting you with that general method before we talk about the shortcut for the leading coefficient of 1 situation, which is probably what you learned in your Algebra 1 course. Because it is pretty easy to do once you're good at it. But that feels pretty good. I mean, that's, I think, a reasonable set of skills that you would have spent, like 85 to 90% of your time in your Algebra 1 class is probably spent doing these kinds of tasks. And I think that's a reasonable starting point. Hopefully nobody saw anything that was wholly unfamiliar, but you might have, and that's okay if you did. Again, some of these things we plan on doing again. For example, the factoring stuff in particular, we'll do this again, whole cloth, because we're going to extend this out to factoring polynomials that aren't just quadratic, and develop a lot of methods to deal with really polynomials of really any size. Now, not every one of those we're going to be able to factor, but certain ones we will be able to, and we'll have to figure out established rules for like when, like which ones can we do it and which ones can't we do it for, and how to show that we can't do it. But that's a big part of the end of first and beginning of second semester is dealing with factoring. And we'll do this for lots of situations beyond just quadratics. So that's a big important piece there. Okay, so starting this second year algebra course, I know that we call it Algebra 3-4 at this school. I just like to call it Algebra 1 and Algebra 2 for first year, second year, rather than by semester. But whatever, no big deal. So we're going to start with the most fundamental building block in mathematics. Well, I should say in algebra, maybe not all of mathematics, but the most fundamental building block in algebra is not the number, it's actually the set. So a set is a list of mathematical objects so those objects could be like numbers, ordered pairs. You could have like functions in your set, or shapes, or lots of other things. You can have sets of lots of types of things. Primarily, when we're talking about sets, we're going to be concerned with numbers and ordered pairs, at least in the first part of the course. And the only criteria for your list is just that none of the items on your list repeat. So if you have an item that repeats, it cannot be a set. But it's basically just a list of things where there's no repeateds. So we have some important notation that we use to describe sets. So typically we name a set with a capital letter. And then before we start our list, we're going to start with like one of these squiggly brackets. And then depending on what our set is, there's kind of two different standard notations that we might use. Let's say the set we're trying to describe is just the counting numbers from 1 to 10. Well, that's a short list of things, right? You could just enumerate that whole list, and that's not difficult to do or time-consuming or anything else. The reason this set is easy to list is because it's finite. There's just 10 members to this. There's an n to the list, which makes it easy to record. This is something that we'd call a finite set because there are a finite number of items inside of that, contained within that set. What if instead of asking for all the counting numbers between 1 and 10, we wanted all the numbers between 1 and 10? What's the difference there? We're including the decimals, right? So we'd have to have like 1.7, 2.65, 3.02695, etc., etc., etc. How many of those do we have? Infinite. So can we list them? No. So we're going to use a different notation in a situation where we have infinite members to our set, because you could write for as long as you want. You'd never be able to list them all because the list doesn't end. So if we want all the numbers between 1 and 10, we're going to describe this with a rule. So typically what we do is we start with what the elements in our set look like. In our case, the elements in our set is just numbers, so we'll just use x to represent that. And then we put a little colon. This colon just stands for the word such that. So this is the set of x's such that. And then we're going to write some kind of rule that describes whether that number is in this set or isn't in this set. Since we're talking about just the numbers between two things, we can just use an inequality to describe this. So if I want all the numbers between 1 and 10, I just want everything that's greater than or equal to 1 and everything that's less than or equal to 10. This again will describe perfectly what's in this set without actually having to list out every single item, because there's no end to that list. Is everybody okay with that idea? Okay. What if we wanted to list, say, the set of even numbers? Is that list finite or infinite? Infinite, right? You can always if you give me an even number, I can always give you one higher just by multiplying it by 2, right? So there's certainly an unlimited supply of those even numbers. Everybody agree with that? Okay. So we're going to use this other notation for an, should probably note that this is an infinite set here as opposed to being finite. I got excited because we started talking about this set of even numbers and I forgot to write that part down. So we're going to use the same notation we used above. For our rule now, are we going to be able to use an inequality? Not to describe even numbers, right? What are we going to need to use? Probably some kind of an equation, right? What is the defining characteristic of an even number? It's divisible by 2, or it's a, like it's a multiple of 2, right? So if I think about that, this is a set of x's such that x is 2 times some number, right? But we have to say what y is. So what else? Even numbers are divisible by 2, and what else do they have to be? Whole numbers, right? So this number y has to be a positive or negative whole number, right? We have a special name for that set of numbers. Does anybody remember the name for that set of positive and negative whole numbers? Is the integers. Does anybody remember that from before? We're going to talk about all these special sets in a moment. You may have or you may not have. It's okay. We're going to do it again today, just in a few minutes. So we'll just put a comma, and then we're going to say y is a member of the integers. So that's a lot of cryptic looking notation there. This symbol is like a curvy E. And you just read it like the phrase is a member of. And this symbol here is the symbol for the set of integers. And if you don't remember, the set of integers is basically the set of positive or negative whole numbers. So notice when I wrote that set out, I put that that ellipsis in there, right? That's what those 3 dots are. What does an ellipsis mean? Yeah, that pattern continues forever. Yep, goes on forever. Okay with that? What if we wanted the set of odd numbers? So again, if we're just looking for a single number, we'll probably start with the set of x's such that. What's our defining characteristic for an odd number? They're not multiples of 2. So can I represent not multiples of 2 with an equation like I did before? Yeah. How can I do it? Okay. Or alternatively, that's a little bit neater, I can just write it as 2y plus 1, right? This will never be divisible by 2 because we're always adding 1 afterwards, right? So we're always going to have an odd number. And that makes things a little bit neater to do it that way. But what you're describing wouldn't be incorrect. Mia, using a not equal to would not be incorrect there. It's not standard, but it wouldn't be wrong. Typically, we'd rather write as an equality than an inequality because it still presents problems of like, how do I find these things? If I wanted to find things inside of there. But it's certainly not a situation where you wouldn't. There are situations where that certainly would be appropriate. Okay. Anything else? No, that's probably fine. Those were tricky enough. Okay. So we've talked about kind of 2 ways to describe sets, whether they're finite or infinite. So let's just do a little example of trying to determine membership. So let's say set A is the numbers 2, 4, 6, 8, 10. And set B is the set x such that 1 is less than x, which is less than or equal. Let's actually do less than or equal to 1 and then less than 10. Okay? So we're going to ask the question then, is 2 a member of A? What do you guys think? Yes. How can you tell? Well, it's right there. It's on the list. So that's pretty easy, right? Is 1 a member of A? No. How can you tell? Yeah, it's not on the list. Even though the 1 is in the digit for 10, we know that that's not the same thing as the number 1. So a digit is different than a number, right? Okay. Is 2 a member of B? Yes, right? Because 2 is greater than or equal to 1, and 2 is also less than 10. Is 1 an element of B? Yes. Anybody object to that? Is 10 an element of B? No. Very good. Why not? Yeah, because if we look here at the inequality here, it's a strict less than. 10 is not less than 10. So even though it's right there on the edge of being included, it should not be included. It is not included in the net set B. Do we feel comfortable at just determining whether something's a member of a set or not? You basically see if it's listed explicitly or if it follows the rule. Okay, good. Let's talk now about special sets. So there's 5 special sets that we do most of our algebra on, at least as a high school student. So the first special set is called the natural numbers. And all of these special sets get a special symbol to represent them. Instead of just using a capital letter A, B, C, etc., these ones are kind of standard. So the natural numbers, we use an N with like a double bar on the diagonal. So that's the symbol that we use for the natural numbers. And the natural numbers is just this set, 0, 1, 2, 3, etc. So it's just these normal counting numbers. But one of the irritating things about mathematics is that as a community, we haven't really decided when we talk about the natural numbers if we want to include 0 or not. So this is something that is not established as a convention, because sometimes when we talk about the natural numbers, we don't mean 0. Now, as a high school student, if we're talking about the natural numbers, my money says that we're talking about including 0. Another place where the natural numbers definitely include 0. How many of us are in a computer science class? Now or ever? Okay? If you're doing any coding, elements in a list are indexed. The first element has got the index 0, then 1, 2, 3. So there's always like the index match is always 1 less than like you maybe think it is. If you've done any kind of programming, you've probably run into a situation like, oh yeah, I forgot that count starts at 0. But any programming language indexes the elements in a list, starting the first one is the 0th index. If you have no idea what I'm talking about, that's fine. It's not important for this class, but it was a place where this matters, and if you've done any computer programming, you know right away what I'm talking about. However, the natural numbers where we're not including 0, once you're outside of high school, is probably the natural numbers that we're talking about, because the most common use for the natural numbers in most of mathematics is as an index, and typically we start our indices with 1 unless we're doing program like on a computer, because it's just more natural. But that either way, it doesn't really matter. That's not like a detail that I'm going to test you on. It's just kind of as an aside. It's a weird aside or interesting aside, but it's just an aside. Okay. Our next set is the integers that we just mentioned a moment ago. And we already defined a moment ago, so I'm just going to skip right to writing this down. And you might be thinking to yourself, like, okay, for the natural numbers, we use this like weird symbol, but it basically just looks like an N. I'm good with that. Why in the world for the integers are we using this Z symbol? Well, mathematics is an international discipline. A lot of the most important mathematics done historically were done in Europe, specifically Central Europe. And Germany was one of the main sources of a lot of really important algebra that was happening, kind of Renaissance to post-Renaissance. And the German word for integer starts with the letter Z. And that's where this symbol is really coming from, is it's descended from that. The next set is the rational numbers. And the symbol we use for the rational numbers is this letter Q with the extra vertical bar in it. Now, this definition is a little bit cryptic looking and probably deserves taking a moment to kind of decode what's written here. In general, as mathematicians, people that write mathematics, we try to write as condensed as possible, so we want to use the fewest characters as possible. It's just kind of the standard what we do, which makes reading mathematics often very difficult because it's very dense. And you look at something that just looks like an alphabet soup of confusion here. But if you know how to read the symbols, it's not really that complicated of a statement. So remember when we do this set notation, this part in front of the colon here is just describing what the things in the set look like. So what does P over Q look like? What kind of mathematical object does this look like? A fraction. So this is just going to be a set of fractions. Okay. So P, what part of the fraction is P? The numerator. So and what part of the fraction is the Q? Okay. And then what does this mean? A member of, right? And then the Z is the integers. Everybody agree with that? And then we have this last part. What part of the fraction is the Q? And the denominator then is not 0. Okay, so we've decoded this symbols into like an English language sentence, right? So we have fractions where the numerator and denominator are integers, and the member are integers, and the denominator is non-zero. What is this basically just describing? Just fractions, right? Things that we can write as fractions. Because we don't write fractions with like decimals in them, right? We don't say 2.7 over 3.6. That's not standard. We want to reduce that into a form where we have whole number over whole number, right? And can we have 0 in the denominator of a fraction? No. Why not? Yeah, it's undefined, right? Something divided by 0 is not a number. Everybody agree with that? Can you have 0 in the numerator?
Yes.
Yes. What's 0 in the numerator?
0.
0. Perfect. Everybody feel okay here? That this weird string of symbols is basically just describing to you the set of all fractions. Or things that can be written as fractions. Really, we should be more specific than that, right? Since something like 0.5, is 0.5 in here? Well, isn't 0.5 the same as 1/2? So we should say the things that can be written as fractions, rather than just maybe expressly saying the set of fractions, right? So quick question here. 0.5 can be written as a fraction, right? What about 7? Is 7 a fraction?
It can be.
Yeah, it can be written as a fraction, right? Because you can just call it 7 over 1. What about 3.65432978842? Can that be written as a fraction?
Over 1.
So not over 1 because it's a decimal, but if you multiply by the right power of 10, a big enough power of 10, it would be a fraction, right? Just like you can in scientific notation. Because you can multiply the top and bottom of a fraction by anything you want, and it still is the same number. But do you agree with that? Like when we make a common denominator, that's exactly what we do. So here's my question for you then. Are there any numbers that we can't write as fractions? Think about your math class last year. Okay, does anybody want to venture a guess? Are there numbers that we can't write as fractions? That cannot be written as a fraction? Okay, so irrational numbers cannot be written as a fraction. Very good. What is the basic fundamental example when we talk about irrational numbers? It's a number you would have used a bunch of times last year in geometry. It's a special number that we give a name to. Pi, right? Yeah. So yes, there are numbers that we cannot write as fractions. We call them irrational numbers. Pi is one of them. But there's a whole mess of irrational numbers other than pi. Yes? So they have to never end and never repeat. So like 1/3, the decimal never ends. But that's definitely a fraction, right? So you also have to have the non-repeated part to it. So examples could be, another basic example is the square root of 2. Radicals actually provide a lot of examples. So I can multiply the square root of 2 by any whole number, and it's still going to be something I can't write as a fraction. In addition, I can take the square root of any number that doesn't simplify to a whole number, and that's also cannot be written as a fraction. So like the square root of 3 can't be written as a fraction. The square root of 4 can, because it's just 2. But the square root of 5, 6, 7, and 8 can't be written as fractions. The square root of 9 can, that's just 3. And then 10, 11, 12, 13, 14, 15 can't be written as fractions. But the square root of 16 can, that's just 4. So the square roots provide a lot of examples of these irrational numbers, the things that cannot be written as fractions. So I'll just kind of do that. Okay? All right. Another question here. So which do you think there's more of? Rational numbers or irrational numbers? So you say the same, and that's probably the common sense answer to make, right? Why do you say the same? Right. So Evan is saying there's infinite rational numbers because you can have an infinite number of fractions, right? Even if you just look at the unit fractions, like 1 over, there's an infinite number of integers that you could pick for the denominator. So that's certainly infinite fractions. It's easy. It should be easy to see that. And just talking about these guys, the irrational numbers we can build out of square roots, there's an infinite number of those because we have an infinite number of, non-perfect squares. So it seems like they're both infinite, right? And they are. Here's the brain boggler for you. Not all infinite sets are the same size. Is that weird to say that?
Yes.
That seems strange, right? How can two things that never end not have the same number of things in it? How would you even tell the difference? Well, I'll tell you what. Let's look at an example here. Let's compare the natural numbers versus the integers. So these two guys by Maddie's description, which one should definitely be the bigger infinite? The integers, right? Because it certainly seems like they contain more stuff, right? Because it has all of the natural numbers and then some other stuff. You guys agree? They're actually the same size. So how can we show that? So we have to think about counting in a different way. So if you want to show two things have the same amount of stuff in them, one way is you could count up everything here, count up everything there, and see that you have the same number, right? That's probably the naive way that we would do when we were little on how to count things. But there's another way you could count things. You could pair things up from each set, and if you're able to pair everything up here with something up from here, they must have the same amount of things also, right? That's what we're going to do here. That's going to be, when we're dealing with infinity, an easier way to count things because there is no end to our infinite count. Everybody okay with that idea? So how am I going to pair up the things with the natural numbers to the integers? So I like 0 to 0, but I wouldn't pair 1 with 1 because what are you going to do with the negatives? But I told you they are the same size, so they do need to have a pair. Okay, then what are you going to put 1 with? Positive 1 with? No. In the integers. What's positive 1 going to pair with? Yes. So you can't, so if we're pairing, you have to have a 1-to-1 pair. You can't do 1 to 2, right? Because now you're showing it has twice as many. But there is the way to show that they have this, to pair them equally. What's another, so you have positive and negatives on the integer side, right? Do you have two infinite things in the natural number side? Two infinite classes of numbers, or types of numbers in there. What would they be? Well, there are no fractions in the natural numbers, right? There are no decimals. We talked about the two kinds of numbers that we're looking for here earlier when we were talking about sets. At the very beginning. In fact, we wrote a set description for these two infinite sets already. How about odd and even? Right? The natural numbers has an infinite number of odds and an infinite number of evens, correct? So I can take the evens, say, and pair them with the positives over here. 2 goes to 1, 4 goes to 2, 6 goes to 3, etc. And I have an infinite number of each of them, so they can all pair up. Everybody agree with that? And then I can take the odds and go with the negatives. So like 1 goes to -1, 3 goes to -2, 5 goes to -3, etc., etc., etc. And now I can pair them up 1 to 1. Yes, sir?
Why is it like allowed though? I thought you had to pair them up with the same number.
No, you just have to pair one thing from over here with one thing from over there. Right? Because now we've shown that everything has a pair. Everybody has a dance partner, right? So they must have the same size. Does that make sense? Like if I have a stack of nickels over here and a stack of quarters over here, I'm just going to pair one nickel with one quarter. It doesn't matter what the denominations are. I can count to see if they have the same number of things. Does that feel okay? Now that's sneaky, right? But once we do it, you're like, oh, okay. Like probably eventually I would have come up with something like that if you tell me it's possible. Because the odd and even part, you just have to find two infinite sets inside of there to pair with the odd, or the negatives and the positives. And I think you would have gotten there eventually. You guys are having good ideas, and clearly had got the idea. So there we have two things that have the same size of infinity, right? So you can't just necessarily say, okay, all the natural numbers are inside of the integers, so the integers have to be bigger. That's not good enough, right? Because here we've shown they are the same. So let's go back and think about this rational versus irrational. So they are both infinite. Do we have any idea of which one do you think is the bigger of the two infinites? I'm telling you right now that one is bigger than the other. And it's not the one you think. Yeah. These ones are the bigger. In fact, how much bigger are they? Between any two rational numbers, there are infinitely many irrationals. Now, we're not going to prove this because it's actually extremely difficult to prove and way beyond the scope of this class. But to give you an idea of, like, if you think about the number line, right? Like the number line, and you put like a dot for every integer, or I'm sorry, every rational number. In between two rational numbers, you have infinitely many irrationals. And even if you find like another rational number in between those two, there's still infinitely many there. Like that's what we're talking about in terms of like the difference in size, which is shocking, right? Because until geometry, you probably didn't even know what an irrational number was, or hadn't actually seen one that you've run into in a daily, like stumbled across when you're trying to do something in mathematics, right? Which is crazy. Okay, so just as an aside here, none of this that we talked about here would be something I would ever expect you to tell me on a test or regurgitate for me. This is all just like very interesting and I think kind of fun and hopefully get you thinking and kind of blow your mind a little bit about how strange mathematics is, but not something I would ever expect you to be able to do again for me. And we'll do this frequently in this course. Like I'll do stuff that's cool and interesting, but not something I would expect you to be able to do again. But I think is important that you kind of see and appreciate, give you a greater understanding and a greater exposure to what like mathematics can look like. That it's not just solving for x. It's like making a clever argument about like, are these two things the same size? And like, how even would you do that when the two things are infinite? Because this is what we've done here. This is like not a trivial thing at all. This is like really surprising, was a really surprising result when mathematicians figured this out. Like this was not at all expected and took a long time and it was very difficult and like very, very famous mathematicians were the ones that did some of these kinds of proofs. So, all right. Back to what we were doing. So we talked about rational numbers. So now we're on to the real numbers. So again, the symbol for the real numbers is just this capital letter R with a second vertical bar on it. So the way I'm going to define this is just the set of x's such that x has a decimal expansion. What do I mean by decimal expansion? Not even repeating, just that it can be written as a decimal. Okay with that idea? So are rational numbers real numbers? Yeah, right? I can write a fraction as a decimal. How do I do that? Yeah, you just divide them. You divide the numerator by the denominator, right? You get a decimal. Everybody's okay with that idea? Okay? So as a fun aside, again, not necessarily something that you'd be asked to repeat. Let's do some more which one is bigger. Because this is fun. Integers versus rational numbers. Yes? You'd think that, right? Because all the integers are contained inside of the rational numbers, right? Turns out they're the same. This was a super surprising result. A mathematician named Gregor Cantor was the one that proved this. Cantor's a very famous mathematician that has a lot of important theorems involved or named after him. I'm trying to look if he's on my Hall of Fame back there. I don't think he is. What if we do rationals versus reals? Here the reals are definitively bigger. This is the most recent of these proofs of like which one of these is bigger. this was one that was, like up until this point, we hadn't found an argument to show that there were different sizes of infinity. This was the first time, like proving this was the first time that happened, which was really kind of shocking to the mathematics community. But this one is definitely bigger. And in fact, it's the same size as the irrationals are. So the same argument that you would make comparing the irrationals to the rationals, you can basically use to compare the rationals to the reals. And in fact, if you really wanted to get down to it, in fact, you don't even have to include the endpoints. If I just want to include the numbers between 0 and 1, still bigger. To give you an idea of how many irrationals there really are, that if you just take that little tiny piece of the number line, that has more than all of the fractions combined, which is just like really kind of a surprising result. And the typical way you would prove this, not at all the proof that was done, but probably the easiest way to do this, is by contradiction. Did you guys remember talking about proof by contradiction last year in geometry? You would have done it for a couple of days maybe. The idea here is to prove, or to do the proof, you're going to assume what you want to prove is false, and then carry that assumption through till you find something nonsensical is happening. Like right now, I say it's sunny outside, or it's not raining outside. So if I'm going to do this by proof by contradiction, I'll say, well, I'll assume it is raining outside. And that means that if I go outside, I should get wet. But when I go outside, I don't get wet. So it can't be raining outside. Right? That's kind of a silly example of what we mean by proof by contradiction. But that's what we would do. So the idea here is, if I can just show that there is no map between the natural numbers and the real numbers, that's enough to show that they're actually, because we know the natural numbers are the same size as the integers, and the integers are the same size as the rational numbers. Just doing this would be enough. And in fact, I'm not even going to do all the way to the real numbers. I'm just going to go just between 0 and 1. Okay with this? So the natural numbers we have like this, right? I'm going to pair this up. Like this, so on and so forth, right? So we'll assume there's a map. If I then take all of these numbers and add them up, I'm going to get something else that's in here, right? But that's not part of my map, because all my maps are zeros and then a single digit. And no matter how you do this map, you'd always be able to add those digits up and get something that wasn't in the set. And that's the gist of the argument. It's a little bit, there's a little bit more to it than that, but in terms of like giving you a flavor of how this was done to show that there is no one-to-one relationship like that, that's kind of the way that happens. Again, not something I would expect you to like repeat for me later, but just I think kind of interesting and hopefully broadens your mathematical perspective a little bit. And our last special set, is the complex numbers, which we use this symbol C with an extra vertical bar in it.